Hello and welcome to this video. This is Group 5 for KIB 1016 Electronic Devices video presentation on the applications of clamper in medical devices. I'm Carmina and I will be covering the applications of clampers in electromyography. My other teammates, Ifra, will be covering on the pulse oximeter, electrocardiogram will be covered by Rokaya, and Farzana will be covering on the electroencephalogram, and lastly, Fatin will be covering on the hearing aid. So, what is electromyography? Electromyography is a medical device which captures the electrical potentials produced by skeletal muscles, typically covering a bandwidth of 20 to 500 Hz, with most energy between 50 to 150 Hz. Technically, the signal is bipolar, low in amplitude, and cannot be directly sampled by unipolar ADCs that accept only 0 until 3.3 volts or 0 until 5 volts. Feeding negative voltage risks data loss or heart rate damage. So, the diagram on the right is a picture of a raw signal from an electromyography without a clamper circuit. Raw signals are unsuitable for direct input into ADCs or microcontrollers due to negative voltages and low magnitude. Signal amplitudes vary widely, from under 50 volts to over 30 millivolts, depending on electrode type. Either it is surface or needle type, and also muscle contraction. Signal conditioning is very important in EMG systems. It readies EMG for digitization by first, it amplifies small signals to a gain of a multiple of 100 to multiple of 1000 into the ADC's input range. So it converts from hundreds of millivolts to 1 volt. Second, it filters out noise below 20 Hz and above 500 Hz. Signal conditioning prepares EMG for amplification and digitization. Most embedded systems, such as microcontrollers, they operate on unipolar ADCs, ranging from 0 to 5 volts. So, to avoid clipping, loss of signal, detail, or heart rate damage, the EMG waveform must be shifted to the DC upwards. Applying a DC offset is achieved by a positive clamper to shift the bipolar waveform outward and keeping it fully within the 0 volt range. A positive clamper, it shifts the entire waveform outward, maintaining the waveform's shape. The circuit components of the positive clamper circuit includes diode, capacitor, and optional resistor. After clamping, the signal becomes fully positive and ready for amplification and ADC input. This is an example of a positive clamper and the waveform of clamped signals. A positive clamper adds a DC offset to an AC waveform using a diode, capacitor, and optionally a resistor. It shifts the waveform so its negative peaks align with 0 volts. How it works is that during the negative half cycle, the diode conducts and charges the capacitor. But in the positive half cycle, the diode is off. The capacitor adds its stored voltage to the input and it lifts the output waveform above ground. So, where does this make a difference? In rehabilitation devices, we use clamped EMG to track muscle activation during therapy in real time. In myoelectric prosthetics, they translate EMG amplitude into control signals, so without clamping, actuator commands would be unreliable. Meanwhile, in human-machine interfaces and biofeedback systems usually used in sports training, they would rely on clean unipolar EMG to accurately interpret muscle fatigue. All these systems depend on practically simple circuits like clamping to ensure performance and safety. That is why EMG signals are small and bipolar, so it is unsuitable for direct ADC sampling. Signal conditioning is important to enhance amplitude, filters noise, and shifts the signal using a positive clamper. This technique preserves waveform shape, protects electronics, and it ensures reliable data capture. In essence, a well-designed clamper circuit bridges the gap from muscle fiber to microcontroller. Thank you. That concludes my section. I'd now like to hand over to Ifra, who will explore clamper circuits in pulse oximetry.
Greetings, doctor. My name is Ifra Padavia, and my metric number is 22102123. My role in this group assignment will be talking about how clampers play a key role in pulse oximeters, which are super common medical devices. You've probably seen them clipped on someone's finger, and it measures their oxygen level and pulse rate. But beyond that tiny display is a very complex electronic process, and even a minor voltage error can affect the accuracy. Clampers help prevent those kinds of errors by carefully adjusting the signals without changing their actual shape, which is super important in medical readings. Let's break down how a pulse oximeter actually works. It uses two different light wavelengths, red and infrared, and shines them through the skin, usually at a fingertip or earlobe. Oxygenated and deoxygenated blood absorb light differently. A sensor on the other side picks up how much of the light actually passes through, and that's converted into an electrical signal. This signal reflects your heartbeat and oxygen saturation and is called a photoplethysmographic signal, or PPG, as you can see in this figure over here. These signals are very tiny, and the problem is they can easily get lost in noise. So the raw data needs to be carefully processed before the numbers on the screen can mean anything at all. So here's the challenge. The electrical signal coming from the sensor is extremely weak, often just a few millivolts, and is super sensitive to changes. Things like body movement, ambient lighting, or even skin pigmentation can interfere, and that's exactly why we need skin conditioning, which involves amplification, filtering, and voltage adjustment to clean up the signal and make it readable by the device's microcontroller. Without this step, the PPG wave might look like noise, and the result could be completely wrong. That's why circuits like clampers are a crucial part of the signal conditioning process. Now, what exactly is a clamper? Although my other teammates have already talked about it, I will mention how the clamper is going to play the role in specific to the pulse oximeter, where it's a circuit that we know that shifts the voltage of an entire waveform either up or down without changing its shape. Imagine you have a heartbeat waveform like a roller coaster. A clamper lifts or lowers that whole roller coaster track while keeping the loops and dips exactly the same. It doesn't amplify or shrink the signal, it just repositions it so that the rest of the circuit, like the ADC, can read it more effectively. This may sound simple, but it's extremely useful in any medical device that relies on capturing small, meaningful signals. How do clampers actually help in pulse oximeters? That's what we're here to find out. In a pulse oximeter, the clamper is responsible for moving the weak PPG signal into the ideal voltage range that the analog to digital converter can handle. Think of the ADC like a camera. It can only capture what's inside the frame. If the signal is too low, part of it falls out of view. If it's too high, the top gets cut off. Both situations can lead to wrong oxygen readings, and the clamper ensures that the full signal from every beat of the heart to every pulse of oxygen is neatly within the frame. It's basically like adjusting the tripod to make sure the entire subject is visible in the shot. Now, why does accuracy matter so much here? This isn't just a technical issue, it's a clinical one. If the signal isn't properly conditioned, the oxygen saturation displayed on the screen could be inaccurate by several percent. In critical care settings or for patients with respiratory conditions like asthma or COVID 19, even a small error in oxygen reading could lead to the wrong treatment. Clampers help protect against these risks by making sure that the signal is clean, complete, and usable. In simple terms, they help doctors and patients trust the device that can literally save lives. So, to sum it all up, pulse oximeters rely on precise electrical signals to give real time measurements of oxygen saturation and pulse rate. And clampers may be one of the quieter components inside these devices, but they play a huge role in making sure those signals are correctly centered and fully readable. Now I'll pass it on to my next teammate.
Hello, doctor. My name is Ruqayya Shakir Hussain, matric number 230840032. Today, I will present on the role of clamper circuits on an ECG. So, what is an ECG? An ECG or electrocardiogram is a medical device that records the electrical activity of the heart over time. These signals are very small, usually around 1 to 3 millivolts, and they repeat in a recognizable pattern made up of the P wave, QRS complex, and T wave. Because these signals are so weak, they are highly sensitive to interference. Things like muscle movement, breathing, or even poor electrode contact can introduce noise, baseline drift, or unwanted DC offsets. Since doctors rely on accurate readings to detect conditions like irregular heartbeats or blocked arteries, we need to make sure the signal is as clean as possible before processing it. Now let's talk about why clampers are needed in ECG circuits. So, before the signal can be analyzed or displayed, it must go through a process called signal conditioning. One major issue with raw ECG signals is the presence of DC offsets, small voltage shifts that can move the entire signal up or down. This becomes a problem for downstream components like amplifiers and analog to digital converters. If the signal isn't centered properly, it can be clipped, distorted, or even missed altogether. To solve this, we use a circuit called a clamper. Its job is to shift the whole waveform vertically so it stays within a safe and readable voltage range. Let's once again look at how a clamper circuit works. A clamper circuit consists of a diode and a capacitor, and sometimes a resistor, as was previously mentioned. It doesn't cut off parts of the signal like a clipper. Instead, it adds a DC level to the waveform, moving it up or down. In an ECG circuit, we usually use a positive clamper, similar to the EEG. Here's how it works. During the negative part of the input cycle, the diode conducts and allows the capacitor to charge. On the next cycles, the capacitor holds this charge and adds it to the signal, effectively pushing the entire waveform upward. This means that the lowest point of the ECG signal is now close to 0 volts, making it much safer to feed into an amplifier or an ADC. To better understand the effect of the clamper, let's look at the waveform. Before clamping, the ECG signal might be centered below 0 volts due to DC offset. After passing through the clamper, the signal is shifted upward as you can see on the diagram, with its minimum value now close to 0. It's important to choose the right RC time constant so the circuit responds appropriately to slow moving ECG signals, as stated by the time domain effect, which usually range from 0.05 to 100 Hz. The clamped signal is now ready to be amplified, filtered, and digitized without risk of distortion. So, why does it matter? Why should we use clampers in ECG devices? Using a clamper in an ECG device helps ensure that we get a clear and accurate signal for diagnosis. It prevents voltage swings that could damage downstream circuits and avoids signal clipping that could hide important details in the waveform. With a stable, properly centered signal, the amplifier can work efficiently and the final digital output is more reliable. This leads to better detection of heart problems, more consistent patient monitoring, and overall improved safety in clinical settings. So, even though the clamper circuit is quite simple, it plays a critical role in making ECG machines effective and dependable. Now, let's look at why clamping plays a crucial role in real world ECG diagnosis. Firstly, the clamper preserves the shape of the ECG waveform. That's vital when detecting arrhythmias, where we need to carefully observe P waves, QRS complexes, and T waves. Any distortion might cause key signs to be missed. Secondly, by preventing baseline drift, the clamper helps keep the ST segment steady. This is especially important in identifying ischemia or heart attacks. It also ensures accurate timing, which is essential for spotting conditions like QT prolongation, where even small timing errors can lead to misdiagnosis. Without proper clamping, voltage spikes could clip parts of the signal or introduce noise, causing false positives or missing critical events, which is absolutely terrible. And in today's healthcare settings, clamper circuits help maintain signal quality with digital processing, including AI powered ECG interpretation. So while it's just a small circuit, its impact on diagnostic reliability is massive. So, in conclusion, even though clamper circuits may be simple, they play a critical role in ECG systems. By stabilizing and centering the signal, they ensure accurate amplification, diagnosis, and monitoring. In medical devices, even small improvements in signal integrity can mean the difference between detection and delay. Engineering precision directly supports patient care. Thank you.
Hi, my name is Farzana Azian, matrix number 24040065. Let's begin with a quick overview of EEG. EEG stands for electroencephalogram, which is a technique used to measure the electrical activity of the brain. It is commonly used in diagnosing neurological conditions such as epilepsy, brain injuries, and sleeping disorders. As you can see the picture in the slides, electrodes are placed on the scalp which will pick up brain signals which are then amplified and analyzed by the device. EEG signals are very low in amplitude, usually around 100 to 10 microvolts, and they contain a range of frequencies between 0.5 to 100 Hz. These signals can swing both above and below 0 volts, meaning they are alternating or AC in nature. Because they are so weak, they are easily affected by noise and need to be carefully conditioned before being processed digitally. Here's the challenge. Most modern signal processing components like amplifier and analog to digital converters ADC cannot handle bipolar signals. For example, an ADC might only read signals between 0 and 3.3 volts. If the EEG signal isn't shifted properly, important parts of the waveform can get clipped, leading to data loss or inaccurate brain readings. That is where clampers come in. A clamper circuit is an electronic circuit that shifts the entire voltage level of a signal without changing its shape. Unlike a clipper, which cuts parts of the waveform, a clamper simply adds a DC level to move the signal up or down. Clampers typically include a diode, a capacitor, and sometimes a DC voltage source. They are widely used in signal processing systems where waveform shape must be preserved. In EEG systems, clampers are used to shift the brain signal into a range that is readable by the amplifier or ADC. For example, if the EEG signal ranges from negative zero point 0.2 volt to positive zero point 0.2 volt, a positive clamper can shift it to 0 volt to positive zero point 0.4 volt. This ensures that the entire brainwave is captured accurately without being distorted or clipped by the electronics. This is especially important in wearable or portable EEG devices that use low power components. There are several benefits of using clamper circuits in EEG signal processing. First, they prevent signal distortion caused by clipping. They also preserve the shape of low amplitude brainwave. Next, they enable accurate digital conversion by the ADC. Lastly, they help protect sensitive downstream circuits from unexpected voltage level. In short, clampers play a key role in ensuring reliable EEG readings. A real-world example would be portable EEG monitors or sleep study headsets, which require compact, energy-efficient electronics. These devices use clampers to condition the signal before it is digitalized and analyzed. Without this signal conditioning, the EEG data collected would be unreliable, especially in mobile or home environments. To summarize, EEG devices captured very low voltage bipolar brain signals. These signals must be conditioned for modern digital systems. Clamper circuits are used to shift the signal into a readable range. This allows for accurate, safe, and high quality brain signal monitoring in both clinical and portable EEG devices.
A very good day, Professor. My name is Fatia Natasha. My metric number is 24040061, and today I will be presenting clamper circuit in hearing aid. First, let's look at the general information about hearing aids. So, as we know, hearing is one of the five senses. Therefore, it is very important that the human ear is able to detect sounds in the audible frequency range. However, in some cases, unfortunately, certain individuals have difficulty in hearing in either or both ears. It is therefore necessary that a device that can help in correcting this will be developed. So, by using readily available circuit components, a hearing aid can be constructed, which will be able to help these individuals. So, as a device, what is a hearing aid? Technically, a hearing aid is a small electronic device that you place in or behind your ear. Hearing aids helps in amplifying the sounds so that people with hearing loss can improve their hearing and speech comprehension. So, as we can see here, this diagram shows a clamper circuit inside of a hearing aid. The clamper circuit consists of a few main components, which is a microphone, transistor, dual audio amplifier, capacitors, a few resistors, diodes, switch, and also a battery. So before we see how clamper circuit works in hearing aids, let us first see the properties that clamper circuit exhibits, which helps in processing the audio inside of a hearing aid. So first is that clamper circuit helps to shift the DC level of a signal. And secondly, it helps to protect against voltage swings. Third, it preserves waveform integrity. And lastly, clamper circuit helps to prepare signals for amplification. So now that we've known the properties of a clamper circuit, let's see how it works together in a signal conditioning and audio processing of a hearing aid. First, enhancing audio clarity. So a well-clamped signal ensures that the amplifier within a hearing aid operates efficiently. This allows for optimal gain control and minimizing unwanted artifacts that could interfere with sound reproduction. So by maintaining a consistent voltage level, which is what a clamper circuit do, the clamper circuit helps to prevent saturation and clipping effects, which can lead to distorted audio output and reduce intelligibility of speech. Secondly, it helps in improving amplification. So clamper circuit plays a role in shifting the DC level of signal without distorting its waveform. So by adjusting the DC components, clamper circuit actually helps to optimize gain control and ensuring that the amplifiers operate efficiently. And since clamper circuit do not distort the waveform, they actually helps to maintain the signal clarity, which is essential for high quality amplification. And lastly, protecting components. So in signal conditioning, the four properties helps in protecting the component as it safeguards sensitive electronics components from excessive voltage swings that could actually lead to damage or malfunction of the device. So by shifting the DC level of the signal, these circuits ensure that voltage variation remains within a safe operating range, and it prevents sudden spikes that could compromise the integrity of the amplifier and other internal circuitry.